Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Jadi kita sudah sampai ke chapter 4 dan chapter 4 adalah tentang simple torsion theory. Okey, ini objektif untuk chapter 4. At the end of this chapter, you all sepatutnya dapat tahu tentang define the circular shaft that is subjected to torsion, dan yang kedua the distribution of shearing strains in a circular shaft, dan apply Hooke's law in torsional theory, dan last sekali awak semua patut dapat kira lah the angle of twist of circular shaft, di mana yang ni later kita akan cover dalam calculation. Okey, untuk chapter 4 teori tentang stress dan strain ni akan di cover dalam slide nombor 3 sampai slide nombor 14. Jadi you all boleh go through slide ni, ataupun nak senang lagi you all boleh tengok video yang saya dah sediakan, dan dalam video ni kalau you faham dah cover overall teori untuk chapter 4 ni. So cadangan saya you fahamkan dalam video dan tak payah lagi tengok slide 3 hingga 14, sebab mostly yang diterangkan adalah benda yang sama dengan apa yang ada dalam slide. Jadi jom kita tengok video lepas ni. Lepas kita tengok video, barulah kita akan buat calculation, di mana untuk calculation saya akan cover dalam video lain. So basically chapter 4 ni cerita tentang stress and strains in members due to torsion. Jadi saya harap awak dah tahulah apa maksud stress dengan strain ni, based on apa yang awak dah belajar sebelum ni. Kalau awak tak sure juga apa itu stress dengan strain, awak better tengok dulu video yang saya dah sediakan dalam separate video yang saya dah upload tentang stress and strain. So lepas you tengok video tu, barulah you boleh start tengok video yang akan saya tayangkan selepas ni. Jadi jom kita tengok video tentang torsion.
Torsion is the twisting of an object caused by a moment acting about the object's longitudinal axis. It is a type of deformation. A moment which tends to cause twisting is called torque. A common example of an object subjected to torsion is the transmission shaft, which is used to transmit power by rotation. This could be the drive shaft and axles, used to transmit power from the engine of a car to the wheels, for example, or the shafts used to transmit power from the blades of a wind turbine to its generators. Let's explore what happens when we apply torque to a circular bar. We can see that the applied torque causes the bar to deform by twisting. An interesting thing we can observe is that individual cross-sections of the bar do not get distorted by the twisting. We can imagine that the bar is made up of multiple individual discs, which rotate relative to each other when the torque is applied, but do not deform. This is only true because the cross-section of the bar is axis symmetric. A bar with a rectangular cross-section is not axis symmetric, and so torsion results in warping of the bar cross-sections. This warping is complex, so in this video we will keep things simple and only consider torsion as it relates to circular bars. Let's fix our bar at one end, and track how a line between point A and point B deforms as we apply a torque to the other end. The applied torque causes the free end of the bar to rotate by an angle phi. This is called the angle of twist. It varies linearly from 0 at the fixed end of the bar to phi at the free end of the bar. We can calculate the angle of twist using this equation. It is a function of 4 parameters: the length of the bar L, the applied torque T, the shear modulus G, which is material property, and J, which is the polar moment of inertia. So, what is the polar moment of inertia? It defines the resistance of a cross-section to torsional deformation, due only to the shape of the cross-section. The polar moment of inertia for a hollow bar, with an outer radius RO and an inner radius RI, can be calculated using this equation. Setting the inner radius to 0 gives us the equation for a solid bar. One neat thing about the equation for the angle of twist is that it gives us a way to determine a material's shear modulus G experimentally. If we apply a known torque to a bar of known length and cross-section and measure the resulting angle of twist, we can use that information to calculate the material's shear modulus G. Torsion generates stresses and strains within the bar, which we need to be able to calculate so that we can make sure our bar won't fail. To figure out how to calculate these stresses and strains, we can start by observing how a small rectangular element on the surface of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted. So the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar in the deformation. It corresponds to this angle between AB and AB prime. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB prime, divided by the length AB. AB is the length L of the bar. We can calculate the length BB prime by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist, theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist divided by the length of the bar. This is actually only an equation for the shear strain on the surface of the bar. But what about inside it? It turns out that the shear strains increase linearly with the distance from the center of the cross-section. So if we define ρ as the radial distance from the center of the cross-section, we can replace r in this equation with ρ to give us an equation we can use to calculate shear strain due to torsion at any point within the bar. That's shear strains covered. But what about shear stresses? Like the shear strains, shear stresses increase linearly with the distance from the center of the cross-section, with the maximum shear stress occurring on the outer surface, as you can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider a small element within our cross-section that has an area equal to dA and is located at a distance ρ from the center of the cross-section. The internal force acting on this element is equal to its area, dA, multiplied by the shear stress tau. We can use this information to work out an equation for calculating the shear stresses. The moments caused by the internal forces acting on all of the elements within the cross-section must sum up to be equal to the torque T. Otherwise, equilibrium is not maintained. We can represent that mathematically by this integral. We know that the quantity tau divided by ρ is a constant, because the shear stress varies linearly with the distance from the center of the cross-section. So we can rearrange the terms and move tau over ρ out of the integral. It turns out that the integral we now have on the right is actually the definition of the polar moment of inertia, so we can replace it with the letter J, and we can rearrange this to get an equation for shear stress. The shear stress is a function of the torque T, the distance ρ from the center of the cross-section, and the polar moment of inertia J. It's quite a simple equation. So we now have equations that allow us to calculate the shear strains and shear stresses. We also have the equation for angle of twist that we talked about earlier. These three equations tell us everything we need to know about a circular bar which is under torsion. So far, we have only talked about a uniform bar fixed at one end with a single applied torque, but shafts are often loaded by multiple torques. This shaft, for example, which is supported by bearings at both ends, is driven by a gear at point B, and in turn drives two gears at points A and C. It is loaded by three torques. Before we can use the equations for shear stress, shear strain, and angle of twist that we just developed, we need to figure out the internal torque at each location along the shaft. The process for doing this is similar to calculating the shear force along a beam, which I covered in a separate video. First, we draw a free body diagram. Then we make imaginary cuts and use the concept of equilibrium to determine the internal torque at different locations along the shaft. This will give us an internal torque diagram that looks something like this. The maximum shear stress will occur in the section of the shaft with the largest internal torque, and can easily be calculated using the equation we derived earlier. I want to end the video by talking about failure due to pure torsion. If we have two bars, one made of a ductile material and one made of a brittle material, and we apply the same torque to both bars, we will observe that they fail differently. The ductile bar fails at an angle perpendicular to its axis, but the brittle bar fails at a 45-degree angle to its axis. We can explain this by remembering that ductile materials tend to fail in shear, and so fracture along the plane of maximum shear stress. But brittle materials are weaker in tension than in shear, and so tend to fracture along the plane of maximum tensile stress. Moore's circle for pure torsion looks like this. We can see that when our stress element is oriented this way, the shear stresses are at their maximum values, and we have no normal stresses. There is a 90-degree angle on Moore's circle between maximum shear stress and maximum normal stress, which means that normal stresses are at a maximum when our stress element is rotated by an angle of 45 degrees. This explains why brittle and ductile materials fail in different ways due to pure torsion.
Jadi kita dah tengok video tadi, dan saya nak rumuskan lagi. Dalam video tadi pun ada formula-formula yang awak tak perlu hafal. Saya nak rumuskan lagi, di mana apa yang awak perlu tekankan adalah formula-formula yang ada dalam slide nombor 10 ni, iaitu maximum shear stress, iaitu Tmax, dan minimum shear stress, di mana yang ni saya akan simplifykan lagi on the next slide. Seterusnya adalah dalam slide nombor 13, iaitu angle of twist bahagian ni, dan dalam slide nombor 14 iaitu formula ni. Yang ni dengan polar second moment of area, di mana kalau saya boleh tulis balik formula-formula tadi adalah angle of twist sama dengan TL per GJ. Apa itu G ni? G ni adalah material shear modulus, dan biasanya nilai G ni akan diberi dalam soalan, dan dia adalah berubah mengikut material. Selain daripada itu, apa yang awak perlu tahu daripada slide tadi adalah polar moment of inertia. Jadi apa itu polar moment of inertia yang awak faham? Ini polar moment of inertia ni, kalau kita faham, adalah reaction force hasil daripada torsion, di mana dia adalah a cross sectional resistance to torsion due to its shape. Jadi dia adalah reaction force yang melawan torsion tadi. Jadi kalau saya boleh lukis balik circle tu untuk hollow, dan ni adalah center kepada circle saya, dan diameter kepada circle belah dalam saya namakan dia sebagai D kecil, dan diameter kepada circle belah luar ni saya namakan dia sebagai D besar. Jadi formula untuk polar moment of inertia untuk hollow, J sama dengan pi D 04 tolak D kecil 04 per 32. Dan kalau metal tu adalah solid, so kita boleh remove yang belah dalam ni, jadikan metal tu adalah solid type metal, dan kita dah tak ada diameter dalam. So yang ni sama dengan kosong. Formula dia akan jadi pi D04 per 32. So simple, awak hanya perlu hafal yang atas ni untuk hollow. Bila awak gantikan D kecil ni, sebab untuk solid kita tak ada diameter belah dalam, so bila awak gantikan dengan kosong, awak akan dapat formula untuk polar moment of inertia untuk solid. So tu cara awak hafal formula ni. So dah dua. So apa lagi formula yang awak kena tahu daripada video tadi? Kita ada formula lain, iaitu maximum shear stress. Iaitu Tmax. So formula untuk Tmax adalah sama dengan TR per J. J ni adalah daripada atas ni. So kalau dia adalah jenis solid, kita ambil formula J sama dengan pi D04 per 32. Dan kalau dia adalah hollow, kita ambil formula yang atas ni, pi kurungan outer diameter 04 tolak inner diameter 04 bahagi dengan 32. So kalau awak perasan, yang formula yang saya tulis ni mungkin lain sikit dengan yang slide, jadi saya cadangkan awak hafal yang ni lagi senang. Dan macam mana nak kira minimum shear stress? Untuk minimum shear stress, kita boleh guna formula Tmin bahagi dengan Tmax sama dengan R1 bahagi dengan R2, di mana R1 ni adalah inner radius, R2 adalah outer radius, dan T minimum ni hanyalah spesifik untuk hollow saja. Sebab apa? Sebab untuk solid kita tak ada inner radius, sebab dia adalah solid circle. So kita hanya ada R2 saja, kan? So kalau kita refer ke atas ni, di mana yang ni di besar ni kita refer kepada outer diameter luar, dan di kecil ni kita refer sebagai inner. So since kita dah pakai kat atas ni, huruf kecil adalah untuk diameter ataupun radius belah dalam, dan di besar adalah untuk diameter belah luar. So kat bawah ni nak senang ingat lagi, kita buat lagi, simplify lagi macam ni. T minimum bahagi dengan T maximum sama dengan, so inner diameter kita akan guna huruf kecil, adalah R kecil bahagi dengan R besar. R besar ni refer kepada radius belah luar. So kalau kita boleh lukis dalam bentuk hollow punya metal, so kita boleh labelkan macam ni. Ini adalah R kecil dan ini adalah R besar. So kalau awak faham konsep ni, awak boleh ingat benda ni, insyaAllah awak tak ada masalah nak ingat formula ni. Dan apa lagi yang awak kena tahu? Kalau awak perasan dalam slide tadi, dalam slide ni, kalau awak perasan kita ada formula ni, di mana formula ni kita boleh pakai di mana-mana je yang soalan tu nak. Contohnya kalau dia nak J, awak boleh guna J ni, bawa ni atas, J akan jadi T bahagi G theta kali dengan L. Kalau contohnya dia nak G, awak boleh mudahkan, awak boleh jadikan formula ni sama dengan TL per J theta, dan seterusnya lah, kan? Kalau perasan daripada sini juga terhasilnya formula angle of twist sama dengan TL per JG. So kalau awak dah hafal yang ni, kalau awak dah hafal formula atas ni, tiga-tiga persamaan ni, awak dah boleh selesaikan banyak soalan dalam chapter 4 ni. So ini sangat penting. Dalam slide ni sangat penting. So tu sedikit sebanyak teori tentang chapter 4. Seterusnya kita akan buat beberapa sampel of questions dalam setiap video yang akan saya sediakan selepas ni. Saya akan buat satu video untuk satu soalan. Jadi awak boleh refer lah setiap soalan yang ada dalam slide ni untuk setiap video.